Hi guys, how you doing? Hope you're well. So in this video, we'll be generating a PWM signal using a 555 timer. So if you didn't watch the last video, I went into a fair little bit of depth about this most popular IC. It was kind of an introduction to it, but also it went into a fair bit of detail that I'm going to gloss over in this video. So if you haven't watched that one, I do recommend checking that one out. So here we have a 555 timer generating a square wave. I'm controlling it using a potentiometer to replicate a pulse width modulated signal. So as you can see, as I change this, as I'm just twisting this potentiometer that I've got right here, you can see my signal is mostly off. As I turn it again now, comes on, and you can see also the LED is also on the output. So I can turn it to be mostly on. The LED stays on fully, halfway. So yeah, so I can generate my own pulse width modulated signal using this potentiometer here. It's basically replicating a pulse width modulated signal. Pretty cool, right? So let's go into how it all works. Without getting into too much detail and geeking out, PWM stands for pulse width modulation. All right, you know what? Let's geek out a little bit. So PWM, pulse width modulation. So it's just a modulating technique where you're obviously adjusting the width of these pulses. So you got a pulse, pulse, pulse. You got 4 pulses here. As you adjust the width, so 100% on, 75% on, 50% on, 25% on. It's a way of controlling how much power you're delivering to a load. Commonly used in things like controlling lights. If you want to dim your LEDs, you can have your LEDs fully on. You can dim them a little bit, dim them a fair bit, dim them a lot, turn them off, right? Same with a motor. If you want to have the motor run at 100% speed, 75% speed, 50% speed, 25% speed. So my plan, and the reason why I'm learning this, is so that I can use PWM to control the power delivery from my solar panel to my battery. So I'm going to have a solar panel, right, and then I'm going to have a battery, and the current going from the solar panel to the battery, I think I could draw a better solar panel than that, right? That's kind of a little bit better. So I'll have a charge controller in the middle here, and it will use PWM to reduce the current that's coming from the panel slowly as the voltage of the battery is increasing, if that makes sense. So that's the reason why I'm learning this. So what we're doing here in this video with this circuit, and apologies about the wires, I usually like to do them all flat like I did in the last video with these ones, but I'm a bit lazy, so forgive me. But I will walk through these. I don't like the looping wires, to be honest with you, but it's fine, I'll walk through it. So in this video, what we're doing is we're taking a solid 6-volt input here from my power supply, and we're pulsing it on and off in order to create a different voltage at the output over here. And so the only important thing to know here is that the duty cycle of the signal, how much the signal is on or off, determines what the output voltage will be. I've got a solid 6-volt signal input here, and then what I'm doing is I'm pulsing it to 6 volts on for a bit and then turning it off for a bit. So if this is 1 period and this is 1 period, so this is on and then this is off, right? So that's both 1 period there. So here now I've got my signal on for half the time and off for half the time. And so what that's going to do is that's going to, instead of my 6-volt output, I'm actually going to get a 3-volt output. And so that's all we're doing here. So if you take this example here, it's got a 5 here. Let's just make this 6. So it's 6 volts. So when it's off here for this period, you got 0 volts output. Here at this point here, you're going to have 1.5 volts output. Here you're going to have 3 volts output. Here you're going to have 4.5 volts output. And here you're going to have 6-volt output. And so what you would do is, for example, if you wanted to output 3 volts, which is half, you would turn your signal on and off fast half the time. So have it on half the time, off to half the time. You can have it same for 75%. That's how PWM works. I could go into a lot more detail, and I'm kind of like hand waving a little bit here, forgive me, but I want to talk more about the 555 timer, so forgive me. Okay, so moving on. Here's the schematic that we used in the last video. The NE 555 timer. We got R1, R2, and C. So in the last video, I had 10K at R1, 100K at R2, 4.7 microfarad capacitor for C, and then a 10 nanofarad capacitor there for the noise. And then we just had a resistor and then LED on the output here, going to ground. If you don't know how they work, I definitely recommend going back and watching that video, because it will help to make sense of this stuff in terms of how the capacitor discharges and whatnot. What you should know is that R1, R2, and the capacitor here, C, they are the ones that determine how long the highs, right, of the pulses are going to be and how long the lows are going to be. So one thing I didn't explain in that video, which I was saving it for this video, is how does this capacitor affect the output, like what's actually happening. And so the way that it actually works is, if you have a look here, here is the waveform of the capacitor. So what you can see is that over the whole total time period, which is this whole period here, I wish this was in different colors, forgive me. So this whole one period here, the capacitor here is charging up, getting to a point, and then discharging. It's charging up and then discharging. So now this is the second period, and then this is the third period. Okay, now as the capacitor is charging, so for this period here and not this bit here, so as it's charging up, our output V out is high. So this is V out, so our output here is high. And then when it discharges over here at this point, if I can do it like this, maybe at this point, then our output is low. And so you can see for our whole period there, the output is actually following the capacitor. So this capacitor here, our output is following this capacitor. So as our capacitor is charging up, our output is going high. As our capacitor discharges, then the output goes low. So I'm trying not to tell you any useless information and information that I perceive to be useless at this stage. So there's a reason why I'm telling you this, and the reason why is that since the output, our V out, right, which is our LED here in this case, since our output is dependent upon the capacitor, we can actually control this V out by messing about with this capacitor's charging time. So if we make our capacitor charge slower and then discharge fast, right, then what that's going to be is that's going to lead to an output where, so let's say this is we're going to have a longer high output and then a short low output. So that's actually going to increase our duty cycle to, let's say, like 80% there. If, however, we make our capacitor, charge quickly and then discharge slowly, then we're going to have a short on period and a long off period. So that will give us a duty cycle there of, let's say, 20%. So hopefully you see how that works. It's very clever how we can if we manipulate the capacitor, we manipulate the output basically. And that is literally how this entire circuit works. So let's go back to our original circuit. So this output here is just outputting a steady square wave, on, off, on, off, on, off, on, off, right? The way that it's doing that is that this capacitor here, C, is charging from VCC here down to the capacitor, and it's charging up. Now if you remember, pin 7 is the discharge pin. So what that means is that this capacitor here now is discharging through R2, right, into the NE555 timer, and then back now down through to ground. If you remember, there's a transistor there. So it's charging through R1 plus R2, but it's discharging only through R2. So what we're going to do is we're actually going to replace this R2 here with a potentiometer, and then that will allow us to actually control both the charging and the discharging time, because obviously it's charging via R1 and R2 and it's discharging via R2. So we just replace R2 with a potentiometer, which is what I've done here. So I've got R1 up here, R2 down here, and then I'm now messing with this R2 down here by changing its resistance using a potentiometer, and then that's going to change the charging time and the discharging time of the capacitor here. The output's then going to follow that capacitor. So what I'm going to do is I'm going to keep everything the same, 10k for R1, 100k for R2, but I'm going to make it a potentiometer. So this time it's going to go, instead of being 100k, it's going to be 0 to 100k, okay, and then the 4.7 microfarad capacitor. But again, watch that first video if you haven't, because you can mess about with these values in order to get a different result for what you want. So we'll keep everything the same. Okay, now I've purposely not explained the breadboard, and the reason why is because other than all the looping wires, which I'm gonna probably have to, I think I'm gonna have to replace them. You know what, bear with, hang on. Okay, I'm back. I didn't want to do it, but I've done it. So it just looks much cleaner, and I can actually highlight to you the different components. So if you look now and compare this to this, which is the original 555 timer circuit, which just produces a square wave, you can see one very different thing. Obviously you got a potentiometer instead of the R2, but you can see here now you've got these two diodes, which look like Zener diodes, but they're not Zener diodes. They're actually these small signal Schottky diode, fast switching diodes they are. So if you look, they're actually going into two different parts of this potentiometer, and I'll explain that in a minute. But very importantly, if you're going to understand how this circuit works, you need to understand how potentiometers work, and it's something that I think isn't common, like it's used in a different way, this potentiometer. So let's just go through it. So the way that we actually wire this potentiometer matters. So in case you didn't know, you've got the potentiometer where it's got the 3 pins A, W, B. So usually you might see this as VCC, and this as ground, and then this as out. That's how they're sometimes labeled. I prefer the A and B, and W for wiper. So this wiper here wipes across this resistive material, and it changes the resistance. So if you've got a 10K potentiometer, 10K, what that means is that from A to B, so from this point all the way around here to here, you have 10 kilo ohms of resistance. Okay, so if you put this wiper here at this position here, what you're doing is you're saying that from this point here, A, all the way around to here, down the wiper and then out to here, you're gonna have 50% of whatever the value of the potentiometer is. So in this case, it'll be 5K, half of the 10K, right? So 5K ohms. So if you have the potentiometer all the way on, so let's say the wiper is now at this point here, all the way around. So it goes from A all the way around. So now this output here is here. So what that means now is that between A and W, you've got 10 kilo ohms. Between B and W, you now have 0 ohms. You just have a short circuit. And this is the part that you really have to understand. So to make that make a bit more sense, let's do it the opposite way. If you put this wiper all the way now down to this point here, so you turn the potentiometer all the way down to 0. What that means is that between A and W, so VCC and out, between A and W, you have 0 ohms. Okay. Now at this point B, if you was to tap your multimeter across at this point here, so let's say you did positive, negative here, then now you would now be detecting all the way around to the wiper here 10 kilo ohms. If it was all the way off. So depending on where you're tapping into, you can tap in at this point and say, okay, I've got 0 ohms. But you tap over here between W and B, and you've now got 10 kilo ohms. If you put it in the middle at 5K, then now here between A and W, you've got 5K. And between W and B, you've also got 5K. So if you look at this potentiometer position, let's say it's like, I don't know, it's like 30%, maybe probably more, it's probably like 35%. So 35% point where this wiper is right now here. So what that means is that between A and W, you've got 35% of the resistance. And between W and B, you've got 65% of the resistance. So to work that out, A and W, we would have 3.5K ohms. And between B and W, we would have 6.5K ohms. So if you used a potentiometer before, you probably would have just connected A and W and then changed the potentiometer and left B floating at ground because you didn't have any need for it. But now you can actually use both of these to the point where it's like you can get two different resistances just by using the A and B. So just in case this didn't make sense, I'm not really a fan of paper stuff. Let's actually do it on the actual breadboard. I'll take my potentiometer here, which is a 10K potentiometer. The output is the middle pin, so I'll just connect that into my breadboard. And then I'll just tap 3 wires here. So I'll do my orange at my output, black at B, and white at A. Okay, let me get my multimeter. Okay, so I'm gonna turn my potentiometer all the way around. It doesn't actually matter where I turn it, but let me put it across my A and B. We're gonna get 10K always. This is always going to be the maximum value across the two pins A and B, okay? Because I'm not using the output, okay? Now, if I just use A and the output, orange, I'm going to get 10K as well because I've turned it all the way around. So 9.8K, okay? Now, I should get 0, if this is a true 10K one, I should get 0.2 kilo ohms if I tap at the output and B, Or since it's all the way around, I should just get 0. So it should just be a short circuit. So there's 3 ohms there when it's turned all the way around. Okay. Now if I put it all the way off, basically, so it's a short circuit between A and the output. Now I should get 0 or 3 ohms. Let's see, 3 ohms exactly. And then from the output and B, 10k. Yep. So now let's put it halfway, and here's where the magic happens, guys. So here between A and the output, I've got 5.1k, and now between the output and B should have 4.7k. So it's not exactly at the halfway point there. So if I go 25% on, basically, then now I should get about 2.53 kilo ohms at the output, 2.7, and then so that means 2.7 minus 9.8 gives me 6.2. So I should get 6.2 between the output and B. 7.1. My maths must be off somewhere. But yeah, cool. So you can see the potentiometer can be used in a very cool way here, in the sense that you can actually tap into different resistances using this. So that's what we're going to do here. Alright, so what we're doing here is we've got our R1 resistor here, and then now we're actually creating a charging and a discharging path for our capacitor. So here now, from my VCC, my capacitor charges through this R1. Same thing we explained here. It's charging through R1, and then it's coming through R2, this variable resistor here, coming to the output, and then going and charging the capacitor. Okay. Then when the capacitor discharges, now it's not going to go this way anymore. It's going to come back this way here to the potentiometer, and it can't go this way anymore because obviously I've got my diode there, reverse biasing it, blocking it. So now it's going to come through this path now, and it's not going to go through this R1 again. It's going to go across this white wire and back to my pin 7 and then to ground. So now this capacitor here is charging through R1 and through my potentiometer, and then it's discharging just through the potentiometer and going to ground via my NE555 timer, because obviously it's not going to go back through R1 because R1 is connected to VCC, it's not connected to ground. So it's going to find ground via the NE555 timer. So what does this look like in the schematic? I left it to last because I think it looks a little bit scary. It did for me, but it really isn't. It's not too bad. So here's the schematic for it. So I've got my VCC, which is 6 volts going into VCC, my reset pin, my out pin, my discharge pin, and so let's follow it. Okay, I've got VCC coming through R1. I've put 1k, but that should actually be 10k. Okay, so it won't make a difference really. But so I've got my VCC going through R1, comes down this way. It can't go this way obviously, so it comes through this diode here, through our potentiometer, and charges the capacitor. So the output then goes high for the square wave, right? Then when it's discharging, comes back through this way, can't go this way because it's reverse biased, comes this way here, and then goes through to the discharge pin and goes to ground. Literally that simple. And my output here is the LED, right? And then this pin, the control pin, we're not using it, so we're just sending it to ground using a tiny capacitor. That's the whole entire circuit. So importantly now, going back to this potentiometer, and this is probably the only part that you really need to understand. Remember, we've got A, W, and B. So what we're doing here is we've got A here, W here, and B here. So this is our output, A, B. So what we're doing is we're charging the capacitor via A and W, and then we're discharging the capacitor via W and B. So as I'm turning this potentiometer, what I'm actually doing, if you think about it, so here like now I've turned it all the way off, okay? So what I'm actually doing is I've just made this point here 0 ohms. So I've effectively, this A to 0, I've just basically shorted this capacitor. So this capacitor is just charging just via this 10k R1. So it's charging rapid, and basically what that means is that it's actually not getting a chance to charge. So you can see here my LED is barely turning on, just flashes on, and then obviously if it's just charged a little bit, it just discharges equally as fast. So now the capacitor here, it's just got this 10k resistance here where it's discharging, and then vice versa. If I now, sorry, it's 100k, isn't it? I don't know why I mentioned here that it was 10k. This should have been 100k and then just 10x all of these, but I think I just mentioned 10k as an example. But for my potentiometer, it's 100k. So I've got 100k now discharging through the capacitor. So if I do it the other way and I rotate my potentiometer now, all the way this way. So now my capacitor here now is at 100k, and then 0 ohms there. And so as I'm changing this potentiometer, so if I make it so it's like 50%, now you've got 50k here, 50k here, so it's charging and discharging equally. And so all you're doing is, you know, if you want it fully on, then you would have it so that it charges very slowly. If you wanted it fully off, you'd have it so it charges very fast. And so that's all we're doing. All we're doing is we're just effectively, we have two paths. We've got our charging path and our discharging path, and we're just varying the resistance. So we could either have, we're splitting up, it's like, how do we want to split this 100 kilo ohm resistance across A and B basically? And so right now it's at 50-50, and then I could make it, you know, at 90-10, etc, etc, etc. So let me just show you that one more time on the oscilloscope, and then that's it. I think you guys are all good with your pulsive modulation. I mean, not your total pulsive modulation, but at least this basic one. So here now you can see I've got these tiny quick pulses, and then as I rotate it to like halfway, we've now got like almost a bit more. There we go. Too much. I mean, we can actually check if we go to measure. So here we've got a 45% duty cycle, sorry. 57 now, too much. 50.7, there we go. So now we've got a 50% duty cycle. We can take that all the way down to 0, or close to 0, so 0.81. Or we can take that all the way up to 100. There we go, 99.9% duty cycle. Really cool, right? What I'm assuming, and I don't know this because, you know, this is the extent of my knowledge thus far. I'm assuming I could use a microcontroller to control this potentiometer to change and vary the resistance. And so once I can do that, I can have a voltage sensor detecting the battery voltage. I can use a voltage divider to detect the battery voltage. And then as the voltage is increasing and it's reaching different thresholds, then have a microcontroller slowly reducing. So like, for example, imagine this now is my charging current. As my multimeter is detecting that my voltage on my battery is increasing, it slowly reduces. So now look, you know, it's pulsing now off my charging current slowly, and then that's going to slowly just keep on dropping down until eventually my battery gets fully charged. And then maybe what I might want to do is I might want to have like a trickle voltage. So, you know, maybe where I was charging it initially at, you know, 100% on, maybe I might want to leave it charging at 5% current instead of 100% current. And so in my head, it seems quite simple. I'm not sure if this is going to be too complicated. I mean, it's taken me quite a while to get to this point here now because I've been struggling with just, you know, the component side of things. But to me, this makes sense. And yeah, man, we'll see. I think maybe my next stage might be to I'm going to try and see how much more complicated I can make this circuit and how much more I can learn from it. That's about it. You now know how to create a pulsive modulated signal. I do really recommend doing these things yourself. I think you just should. One thing I did enjoy was, I don't know, like the LED, our eyes are quite insensitive, right? Our eyes are not sensitive to the changing of the LED lights. So I think our ears are more sensitive. So I'm going to annoy you. I'm just giving you fair warning. I'm going to stick a buzzer in. It's going to be annoying, you know. Maybe if you have headphones, turn it down. And so you can actually, like, it's like a bit like an ECG. You can hear it a lot better. So as I turn this all the way down, there you go. So I don't know if you guys can hear that, but you can hear these tiny 1% pulses, right? But now if I make it 100%, it's just on the whole time. Put it down to 50%. $25. But yeah, I found this to be quite useful. It reminds me of an ECG. I actually, just to annoy my wife, I just left it on for like 3 hours, just doing this basically. Cool. Alright guys, that's it for me. I won't take up any much more of your time. Thanks for watching, and I shall see you guys in the next one. Hopefully we do a more complicated, hopefully we do a more complicated pulse modulated signal. If not, I'm going to crack on and carry on with trying to charge a battery. Cool. Take care, guys. Bye bye.